Hello, everyone. My name is Sunny Chatterjee. I'm an engineering manager in the C++ team at Microsoft. And for the past few years, I have been working on static analysis. So today, unsurprisingly, I'm going to be talking about how we used static analysis principles to close the gap between Rust and C++. Before I move on to my talk, I would like to welcome all of you to CppCon. We have a table at the expo hall where you could meet the Microsoft C++ team and ask questions on the demos and the new features that we have announced and interact with us. There's also a chance for you to win a Microsoft Flight Simulator by filling in a survey. I have a link for it at the end of this slide. So in this talk, I'm going to be talking about static analysis in Rust. I'll share my first learnings on Rust. Then I'll share the challenges of bridging the gap between the two languages. I'll talk about the data from Microsoft production code. We have been using static analysis in Microsoft production software for a number of years. It's used to analyze millions of lines of code. So it's always fun to talk about some of the bugs that we see in production. Next, I'll cover where we are today in terms of our tooling and what's next for the Microsoft C++ static analysis. In the end, I leave you with some helpful links that you can refer back to after my talk to dig deeper into any of these topics. So let's look at what static analysis is. Well, static analysis is a technique which reads in C++ code, and it applies some logic to look for defects and reports these defects at compile time. So the interesting thing to note here is that we find defects at compile time without the need to execute the code. And our focus today is primarily going to be on local static analysis, where a local static analysis tool doesn't have visibility across function boundaries, and it considers each function in the translation unit in isolation. And there is a reason why we'll be focusing on local static analysis tools today. One is that local static analysis is fast, and we can apply this technique at scale. What it means is that we are able to provide defects to the user as he's typing his code or saving his work or even building. So there's a lot of value that we can provide before bugs get checked in. The second reason is that over the past few years, we have applied a few techniques to make local static analysis scale. So for example, we can look at the function boundaries, we can look at the signatures on the functions and infer a lot about what the function is trying to do. We can look at the attributes. We can also look at things like standard Win32 APIs whose behavior can be taught to the local static analysis tools. And using these heuristics, we can really make it an effective tool, and we can bridge the gap, for example, with a global analysis tool. Now, why that is important is our objective is to find and fix defects at the earliest point in the development cycle. If you can do that, then you can save a bunch of dollars for the company because bugs are cheapest to fix before they are checked in. It's also in alignment with one of our company values. We want to be committed to quality, and static analysis definitely helps play a role in our commitment to quality for our customers. Next, I'll talk a little bit about Rust. So before I move on to this, I was curious to learn how many of you have used Rust either as a programming language to play around or in real production software. Unfortunately, I cannot make it very interactive. So if you can share your experiences in the chat window, I would love to read about them and learn about them after my talk. So Rust is essentially a programming language that empowers everybody to build reliable and efficient software. That's the definition you would find in Rust Lang. It's a great resource if you want to start looking into Rust. So the question is why we looked into Rust. Well, I've been doing static analysis for a number of years, and for decades, I've found that C++ is primarily focused on performance. Performance is a big reason why people would choose to use C++ in their performance-intensive applications. However, we have seen a shift over the last few years where we have been stressing more on how people should be writing modern, safe C++ code. We have been working with the C++ core guideline editors and implementing some of the guidelines in our C++ code check. So essentially, customers and security researchers in our company, they have been telling me that they want to see stronger safety guarantees in C++. So there was an internal survey done at Microsoft for teams that were adopting Rust as pilot projects. And one of the key reasons for its adoption was correctness. So it's not just about performance and safety, it's also about correctness. People are increasingly expecting high fidelity from your compiled code. If a code is compiling correctly, they would expect it to execute as desired. There is a log from Microsoft Security Research Center I have on this slide that you can refer back to after my talk that goes into, provides a high-level summary of why Rust is a safe language for systems programming. So the challenge for us was to see if we could use the power of static analysis tools to bring some of the safety guarantees of Rust into C++. So Rust compiler does a lot of its checking at compile time, and it's very similar to what we do with static analysis, where we do these checkings at compile time. It seemed like a natural fit, so it was interesting to explore this territory and share the learnings with you all. So let me go into my first learnings as I started looking into Rust last winter. So in Rust, safety features are built in. What it means is if you're going to be breaking any of the safety features, your code will not compile. You cannot run that code. You cannot ship that code to your customers. Now, what I've seen is in C++, we have these checks spread across the tool chain. The tool chain does offer these checks, but first, these are not enforced by the compiler. And second, even if you have configured them for your project, it's easy for you to turn these features off, and your code would still compile and run just fine. And the second learning for me was there isn't necessarily a 1:1 mapping between every Rust safety feature and C++ core guidelines. And that's by design. Several Rust rules are restrictive for existing C++ coding practices. And our objective was not to just copy every Rust rule in C++. However, we wanted to look at the broader picture. We wanted to look at the big buckets of safety and correctness. And we wanted to bring over what made sense in the landscape of C++. So this isn't an exercise to take every Rust rule and bring that into C++. So the challenge for us was obviously to bridge this gap. So we started identifying actionable safety differences that could be statically checked. We also wanted to see if our static analysis framework, the engine that we use to power the code analysis checks in Visual Studio, the C++ code check rules, if the engine could be used to write some of these missing safety checks. And lastly, we also wanted to keep an eye out on the C++ core guidelines. A lot of thought has gone into these guidelines. So obviously, it was a very interesting finding for us to figure out how much of the Rust rules are covered in the core guidelines. So the exercise we did was to go over the big buckets of safety and correctness rules in Rust. And when we tried finding corresponding rules in C++, whether they are in the standard or the core guidelines. And lastly, we wanted to see how much of these are available in Visual Studio today, and if not, what it will take to implement these missing checks. So next, I'll talk about some of the big buckets we looked at. So we looked at casting, we looked at switch statements, we looked at smarter loops, we looked at smarter copying, lifetimes, mutability. So I'll first talk about casting. So Rust does not allow implicit casting among primitive types. What this means is if you take a function that takes a 32-bit integer and tries to convert it into an unsigned number, Rust compiler would error out saying you've attempted a conversion from signed to unsigned. Similarly, if you have a function that takes a float and tries to pass it to a function which expects an integer, that conversion is not allowed by the Rust compiler. It's interesting to note that C-style casting is allowed for some of the types. And as you can see in this example, you have a C-style cast that converts this 8-bit, this 32-bit integer to an 8-bit. And it has the usual problems of C-style casting where you can wrap around it, you can change the signedness. However, no conversion is allowed from an integer to a bool. So here's an example where we're trying to use the conversion from integer to a bool, and the Rust compiler does not like it. So it will not allow you to convert an integer to bool. Similar, you can't use this as a Boolean expression. You have to convert that a, which is like a integer not equals 0, to convert the integer expression to a Boolean before you can use that in an if conditional block. Safe casting in Rust can be achieved using the try from and the try into traits. So here is an example where you have a try from trait where you're trying to convert a 32-bit integer into an 8-bit value. And if the value fits into that range, you will assign that to your variable b. Otherwise, you are assigning a default value of 42. So you're using these traits to essentially perform safe casting. Next, we looked at the casting rules in C++, and we have this type safety profile in the C++ core check, which is built upon the C++ core guidelines, which does provide a whole bunch of rules around how you could do casting safely. It forbids using reinterpret cast, by which you can convert any integer to a pointer. It doesn't want you to use a static cast for doing down casts, because you can actually there can be a data loss. So we have created these types in the GSL guideline support library called narrow and narrow cast that you should be using for downcasting. Similarly, it says don't use a const cast to cast away constness. So there are these whole bunch of rules that if you go to Visual Studio and try the C++ code check type safety profile today, that would lead you to use casting in a safe and correct way. So we were pretty happy to see where we were in terms of the casting rules in C++. So the next bucket we looked at was switch statements. So in Rust, it has a pattern matching construct that covers similar functionality to C++ switch and more. It's a match statement where in this example, you see you have a 32-bit integer and you're trying to match the values 1 and 2. And if you omit this third statement, which is like the equivalent of C++ default, then the Rust compiler will not compile this code because it wants you to check for every possible value of that integer. Similarly, you have an enum here, which has 3 values, A, B, and C, and you have to explicitly check all 3 values of that enum. Otherwise, your code in Rust will not compile. So in C++ core guidelines, we did find a number of rules that would lead the programmer to use switch statements in a safe way. For example, there is a rule that states switch statements over a non-enum type should have a default. Switch statements over an enum type should either have a default or it should cover all possible cases. And similarly, it wants you to mark all the implicit fallthroughs with the C++ 17 fallthrough attribute. It's interesting to note that Rust does not have the fallthrough in matchers, but in C++ we do, but our intent should be clear. We should be using the C++ 17 attribute. So next, I'll do a demo of this of these checks in Visual Studio. We just built some of that were missing. So here is a code where we have a function that takes an integer, and it has a switch on that. It has 2 cases. It doesn't cover anything other than the value of 0 and 1. So here you will see a green squiggle as you are saving your work. You will find a warning that says the switch statement does not cover all cases. Consider adding a default level. Similarly, here is another example where you would find here is a function foo that covers a few cases for an integer. It also has a default, so that's great. However, case 1 here is interesting. It has an if condition and an else part. So in the else part, we have an explicit fallthrough. However, in the if part, we do call a function, but there isn't an explicit fallthrough. There is an implicit fallthrough happening from here to case 2. So we don't know whether this is intentional or it's a simple programming logical error. So we have a green squiggle here that's provided by the background code analysis run. If you hover over it, it'll tell you that, hey, this is an unannotated fallthrough between the switch levels. So what you want to do here is either add an explicit C++ 17 attribute. So it could be something like and then you save your work. And what happens is once we make it explicit, that green squiggle disappears. So we looked at casting and switch statements. We'll look into smarter loops next. So in Rust, we do not have C-style for loops, because you all know that in C-style for loops, it's error prone, it's complicated. We can read past the bounds of the container. So what Rust wants you to do is it wants you to use ranged checked iterator pattern, and it wants to force loop variables to the loop itself. So it's very similar to the range for loops in C++. So here's an example from the Rust book where you are basically going through the elements of this array, but the syntax is very, for those of you that are familiar with C++ range for loop, you can see that this is a simple C++ range for loop. Similarly, you can do more complex operations. You have a sequence from 1 to less than 11. You can reverse that sequence and step down by 2. And all of that can be done in a way where it is range checked. So I've got a comment here saying that I should be zooming into Visual Studio. I'll be doing that for my next demo. So in C++, we do have a number of rules around loop safety. So it says that we should be flagging loop variables that are declared outside the loop. So here's an example where you have a Cstyle for loop with the loop variable declared outside the loop. And what we really want to see here is that loop variable should move into the loop. It should be scoped within the loop body and shouldn't be used after the loop. Similarly, you have an if statement where the condition of the if is computed outside the if, and we want to see that moved inside the if. Similarly, there is a rule in C++ where it wants us to flag reuse of loop index variables. So you have a loop index variable I here, which is used in 2 loops, and it's reset in the second loop, and it's not used in between the 2 loops. And there's no reason why that shouldn't move inside the loop body. So we do have these rules in the guideline to use loop safely. So the other example that's interesting is we want to convert Cstyle for loops into for range loops. So here is a typical Cstyle for loop example where we're basically going from 0, it's less than the size of the vector, and then you're indexing it by that variable I. In the second pattern, it's more predictable where we have the begin and end. So we are still using naked iterators, and it's still possible to read past the end of the collection. If you are using naked iterators, it's not range checked. The third format is what we would recommend, where you're using a range for loop and it's impossible for you to read past the range of the vector. So in this particular case, we want to issue a warning that says, hey, don't use Cstyle for loop, use for range instead. So here, I wanted to spend some time on this example to show you how a static analysis tool would reason about code and then come up with these warnings. So what the tool will first see is, okay, it will note that this loop has it has a loop variable I. It's just one loop variable it needs to track. And the condition of the loop variable is bound by the size of the collection. So it's less than the size of the vector here. Next, it will see that the increment expression is a simple increment by 1. And next, it will check that there is the only way the loop index variable is used is for a simple access. There is no funny things happening like pointed arithmetic. It's not used to access with a +1 or +2. There is no assignment happening to it. And lastly, it will also make sure that we are not doing any side effects on that collection. So for example, if in the loop body we had a pushback operation on the vector, that would cause interesting side effects. So if none of these are happening, then the tool can pretty reasonable confidence warn that, hey, you really need to change this Cstyle for loop into a range for style for loop. So we covered casting, switch statements, smarter loops. Next, I'll be talking about smarter copying. So the interesting thing about Rust is it's moved by default, and copying semantics must be explicit. So this is very different than C++, where in C++ we have a language which is copy by default, and move semantics has to be specified explicitly. And move by default is indeed a big part of Rust's memory management techniques like lifetimes, ownerships, borrowing, and it helps Rust prevent memory leaks. So here's an example where you have a big structure that you're assigning to an object A, and then you're assigning A to B. So what happens after this statement is that A can no longer be used in Rust because the contents of A has been moved into B, and that would result in a compiler error. If you want to copy explicitly, what you want to do is you want to use a clone here, and that would copy the contents of A into B. So in C++, we wanted to see what the side effects of these copy are. And one interesting thing that came up was the inadvertent copies that happen in the range for loops. So we wanted to flag range for loops that do unnecessary copying. So here is an example where you have a vector which has a complex type, and that complex type, imagine it's like an expensive type. It has then you are iterating over that type in a range for loop in C++, However, inside the body of the loop, you're not mutating X. It's never written into. So what we really want this code to look like is something like here below, where we want to change this X to be a const ref because it's never mutated, and there's no reason why we should be doing that expensive copy. So in this particular case, the static analysis tool would first look for that expensive copy in the range for, and then it would suggest that it be marked as a reference. It also wants to make sure that the data type is expensive. So it doesn't warn if the object is just a view or a smart pointer, because those are, passing them by value. Taking a copy is just fine for views and smart pointers. It also wants to make sure that the loop variable is not mutated inside the loop body, because if it were, then you couldn't suggest a const ref. I'm going to demo a check that we wrote in Visual Studio for this particular check. So you have a range for here, you have a large struct and you have a small struct. Let me enlarge the fonts a little bit. So you have a large struct and you have a small struct, and then you have a function that takes a const ref to a vector of large struct, and it takes a const ref to a vector of small struct. So the very first range for that you see here is where we are iterating over that large collection. However, we are calling a function that does not mutate that data. So this copy that is happening here is completely unnecessary. So we get a green squiggle here that says, hey, you're doing a potentially expensive copy of variable in the range for loop, consider marking it as a const reference. So what it really wants the user to do is mark this data as a const reference. And then once you save your work, then background code analysis should run in the background, and you should see that this green squiggle should disappear. However, in the next for loop, we are iterating over the collection of small structs, and we don't ask you to mark this as a const reference because this is really not an expensive copy. So you should be good there. Similarly, in the next example, you have a for range for loop where you're iterating over that large collection, but you're actually writing into each element. And because it's mutating, you need to take this as a copy, and we wouldn't be warning here. Similarly, when you are passing it to a function like take int mute, which takes the element by reference, the static analysis tools would conclude that because that data is passed as a reference, there is a write happening to it, and it would not ask you to mark this element as a const reference. So the next tool we looked at was suggesting using const autoreference instead of auto when assigning from a reference. Let's look at an example. So Rust copy semantics are explicit. So if you have a function that returns a reference, and if you assign that to a variable A, then the type of that variable is a reference and no copy happens in Rust. However, in C++, if you use an auto keyword on a value and if you assign it to a function that returns a reference, then there is an implicit copy happening from that reference to that object type. This is different than if the function returns a pointer, where the auto variable does get the type of the pointer. So some of the ramifications of this is it can be confusing to new C++ users. It's arguably inconsistent with pointers. And it's easy to make an expensive copy by forgetting the reference on the auto. So I'm going to demo you a check that we wrote in Visual Studio to find these values. So here you have a large struct, and then you have some struct which encapsulates the large struct. It has a member function that returns a const reference to that large struct. So in foo, what you have is a const reference to that some struct, and you're basically calling that member function get large struct, which returns a const reference, and you're assigning that to a large struct. And there is an implicit copy happening here. However, you're not writing to the large struct in the body of the function. So our analysis tools would flag this as a green squiggle, and it would say, hey, you're assigning by value when a const reference would suffice. Use a const autoreference instead. So what it really wants you to do is add a const here and add a ref here, and then you should be able to save this, and you should find that the green squiggle should disappear. This is, again, interesting. The next case is where we have a large struct where we are passing a reference and there is a copy happening implicitly. However, you will find that we are writing to the field of that struct. So we are not warning here because we are in fact mutating it, and a copy is necessary. The last example is around lifetimes, where you are calling some struct, which returns a temporary object of type some struct. However, it's interesting to note that we are not binding this temporary object to anything on the left. What we are instead doing is we are calling this member function on that temporary object, get large struct, which returns a const reference to a data member of that temporary object. And in this case, a copy is necessary because if you mark this as a const reference, then you are basically going to be referring to a data member of a temporary object, which would not be valid after this statement is executed. And that's going to be bad. So in this case, the tool recognizes this pattern, and it would not ask you to mark this as a const reference. So we looked into casting, switch statements, smarter loops, smarter copying. Next, we will talk a little bit about lifetimes. So Rust's memory model makes it hard to accidentally leak memory. In C++, however, we have a set of rules on the lifetimes profile that statically checks against invalidated iterators. So if you go to the Visual Studio today, and if you select the C++ code check lifetime profile from the code analysis, you would be able to find these errors in your code. However, it's interesting to note that when we dug a little deeper into what sort of lifetime checks are available today across the tool chain, here is one particular rule where we didn't find a check from any of the tools. Like, here is a guideline that says, no checks for never. There are no checks for never returning a pointer to a local. So here is an example where you're trying to build up the contents of this vector, and what you're doing is you're pushing in the address of a local on this collection. So obviously, after this function returns, this address would point to invalid memory. And none of the existing lifetime checkers were able to find this pattern. So there's definitely scope for improvement, where we would need to detect these kinds of leaks in the static analysis tools. So I would like to demo you a lifetime check for invalid iterators. So here is a dangling iterator pattern where you have a vector, it has 3 elements, and you are taking an iterator on this, which is pointing to the beginning of the vector. And what you're doing is you're trying to dereference the iterator and write to it via the iterator. And this is fine because the memory is still valid. However, on line 8, you would see that you're doing a pushback operation on that vector. And when you do the pushback, the memory layout changes. So what it means is that iterator is no longer pointing to a valid piece of memory. So when you're trying to dereference that iterator and write through it, you'll get a green squiggle that says, hey, don't dereference a pointer that may be invalid. And it'll tell you that in line 8, this result may have been invalidated. So what you really need to do here is you have to assign this iterator to the begin block again. And that way it will point to a valid piece of memory again. And so when you save your work, you should be able to see that this warning from the lifetimes profile should disappear. These checks are already available in Visual Studio today. So you can go to your project, you can go to properties, and you can select the C++ core check lifetime rules from code analysis. All right, so we covered lifetimes. Next, we'll talk a little bit about mutability. So Rust is immutable by default. What it means is that if you have a variable that's assigned a value of 3, and if you're trying to do a assign plus on that same variable, that's an error in Rust because A is immutable by default. If you want to mark it as mutable, you have to use an explicit keyword in Rust. The second interesting thing I noticed about Rust is it forbids having a mutable and an immutable reference to the same object in the same scope. And by avoiding a mutable and immutable reference, Rust can help make certain guarantees around data race safety. So here's an example where you have a variable which has a value 3, you have a immutable reference to it, and then you have a mutable reference to it, and then you're incrementing its value via the mutable reference. Next, when you try to pass the immutable reference, the const reference to your function, the Rust compiler would complain saying, hey, you're borrowing an immutable version while it's mutated above, and that's invalid. It does not allow you to do that. In C++, marking an immutable data as const is viewed as a good programming practice. A few years back, we rolled out a series of checks for const correctness. So all those checks are part of the C++ code check rules in Visual Studio. An example would be like you're assigning to a variable only once in your function. If you're doing that, we would encourage you to mark that variable as a const. However, I wanted to revisit this example from Rust, where you're trying to access mutable and immutable reference in the same scope. A same code written in C++ is variable assigned to value 3. You have a mutable reference and a const reference to that variable. You're incrementing its value via the mutable reference, and then you're printing its value via the const reference. So the question remains, do you really expect to see a 4 here? And it can be argued that that may be a reasonable addition to the checks where you see this pattern. You maybe you want to highlight this and say that, hey, did you really mean that? So that's a check, again, that does not exist today, but that's something worth exploring. So I wanted to summarize the exercise that we just did here. So we tried bridging the gap between the two languages. We identified actionable safety differences. We covered the big buckets of safety and correctness. We also explored rules from C++ core guidelines that cover many of the big buckets we looked at. We looked what exists in Visual Studio code analysis today, and for missing checks, we tried adding them in the latest preview. Obviously, we also identified more work that is needed in the tool chain. So we could be doing more checks in the loops, like we could identify, for example, loop invariants and suggest moving them out of loops. We could be improving our lifetime checks that we have in the C++ lifetime profile. Similarly, we could add checks around borrowing whenever we see a borrowing semantic in C++. And lastly, I also wanted to talk about this where, we really, what we are missing today is a strict mode in the compiler that would enforce some sort of safety guarantees at compile time. Right? You have all these checks spread across the tool chain. However, it's also easy for a developer to go and turn these rules off. So the code that you run and you ship doesn't have any sort of safety guarantees. It depends on what checks you ran during compile time. So it's interesting to think about a strict mode in the compiler where you would not be able to turn some of these rules off. However, what you get as a result of that is you get some safety guarantees. Next, I wanted to share some data from Microsoft production code. We run the static analysis tools in Microsoft on millions of lines of shipping C++ code. And from time to time, we find interesting bug patterns, vulnerabilities, logical errors. So it's always fun to come back and talk about these patterns. So next, I'm going to share a security vulnerability we found in one of the production software at Microsoft recently. So you have a message handling function that receives memory, and it has two parameters, P data and CB data, which are like the destination buffer receiving the memory, and CB data would be the count of bytes of data copied into the destination buffer. And you have here two variables, pmem data and cbmem data, which are the source buffer and the count of bytes on that source buffer. You have a call to this API called getMemory, and getMemory fills in your source buffer with the count of bytes of elements of data that is copied into the source. And then you're trying to use the Win32 API to copy memory data from the source buffer into the destination, and you're copying CB data. And you're actually copying it from an offset, which is current mem position, and you're incrementing that current mem position. Here you get a static analysis warning that says, hey, you have a potential read overflow using pmem data. The buffer is apparently unbounded by buffer size. Why? Because pmem data has cbmem data elements. However, you're copying CB data here from an offset, and you don't know whether you can copy CB data elements from this offset, whether that's within the bounds of cbmem data. So what you in fact have is we added a check to check for that bounds, and then this static analysis warning should disappear. this function still has a problem, which is the main vulnerability here. The copy memory is not checking the bounds of the destination buffer. So what you result in is a missing bounds check here before the call to copy memory has resulted in a remote code execution vulnerability. So how did we mitigate that? So it turns out if you're using C++ modern types, if you're using safe types, you can mitigate that even without fixing the actual problem, which is what I'll show you in my next slide. So if you look at the security vulnerability mitigation, you will find that in this new function, receive memory, we have first changed the destination buffer to be a span. So a span, for those of you that are not familiar, is it basically is a pointer and a length into a sequence of bytes. So by making it a span, we can always know what the length of this data is. Next, we changed the type of the source buffer to be a span as well. Then we did the usual stuff. We got memory on that mem data. We asserted that the memory we got was actually valid. Then we tried to check for the readable length. We made sure that you can read from here successfully. And then we created a subspan from the source buffer where we wanted to create this subspan from the offset, and we wanted to create this subspan of length CB data. And then we pass this to a function called GSL copy. And what this function does is it tries to check that the size of the buffer pointed to by data is greater than or equal to the size of the source buffer. And if the size is smaller, then it would terminate the program. So if you're using these types safely, what you can do is by moving to the GSL types, we now mitigated this security vulnerability, change that from a remote code execution to a denial of service, which is a lot more preferred state to be for our software. So the second example I have here is for performance. So here is an example, again, where you had this common class table. It's a really expensive type. It has lots of fields in it, and you're iterating using a range for loop. And if you inspect the body of the loop, you would find that the only thing that you are doing here is you're accessing some elements from item, and you are then manipulating that data and returning the value. There is no mutation happening here on the item. So this is an expensive copy, which would result in less performant code. So static analysis would come in here and it would say, hey, you really ought to mark this item as a Const Auto ref. So I wanted to talk about where we are today in terms of our tooling. So static analysis tools have been in use at Microsoft for close to 2 decades. It's used to validate millions of lines of production C++ code day in and day out. And some of the checks, in fact, all of the checks that I demoed today are available in the latest version of Visual Studio 2019. You can run these tools by using Visual Studio IDE. The checks will run in the background as you're working on your project, and they would show up as green squiggles, and it'll point to the problem in your code. And once you fix the code, the green squiggles should disappear. We also have a limited number of fixits for a limited number of checks. If we get good feedback, that's also something we are open to adding in the IDE experience. You can also run code analysis as an explicit task, so you can run it on file or on a project or on your solution. Similarly, you can also configure code analysis to run in your build system, whether you're using CMake or MS Build or NMake style projects. Ultimately, code analysis takes in a bunch of additional options to your compiler command line, so you can always configure your build systems to run code analysis as you're building your project. Now, in terms of how we do these checks, simple checks are built upon an abstract syntax tree or an AST layer. And we have a plugin model for writing checks that consume the data from your program that's compiled by the C++ frontend. Right now, this plugin model is not exposed externally, but I'll be talking more about this in my next slide. If there is enough interest in the community, that's something we can definitely look into. And some of the checks require data flow and path sensitive analysis. Again, for path sensitive, we have a CFG or a control flow graph layer on top of the ASTs. And we have a lot of libraries doing things like alias analysis. We have a constraint solver to do path simulation correctly. And there's been like 10 plus years of research that has gone into this framework. Again, it's not something that's available to you as an today, but that's something I would love to get some feedback on. If there is enough interest, we can definitely talk to the lawyers and make it available for the community. So what's next for Microsoft C++ static analysis? We definitely want to drive more safe C++ policies using static analysis. There are a whole bunch of security rules that will be coming out in the next preview that would catch misuses of variance, enums, H-result value types. So those checks are already in the pipeline. We also want to roll out high fidelity rules for detecting memory errors. So anything we can do for bound safety, we would be adding those checks. If you see a pattern in code where you have a raw pointer and a length, and if you can safely replace that with GSL span, we would have rules that would suggest you to move to a span for those kinds of code. We also want to improve our lifetime checking. We've got feedback where there are certain classes of false positives that we need to fix. And like I said, Rust has a lot of cases on lifetimes and borrowing that we could build into the C++ lifetime profiles. So we'll definitely be investing in that going forward. The other objective for us is to meet the tooling needs of the community as the language evolves. So for example, with C++ 20, we re-implemented the GSL span in our guideline support library so that it's compliant with the standard span. We also rolled out a bunch of rules when you're using coroutines, which is another C++ 20 features, because turns out when you use coroutines, you can run into interesting problems around concurrency errors, around lifetimes, and we've added a bunch of checks in Visual Studio that would find these issues for you when you're using a new language feature. So as the language evolves, we want to make sure that we can detect any misuses of any new features that get rolled into the language, and we'll continue investing there going forward. The other library we care deeply about is the Microsoft Guideline Support Library. So this library had the initial implementation of GSL span, which played a big part in the standardization of span. This library has types that allow you to mark types as not null. And if you're then seeing a null value, we would throw an error at runtime. It allows you to use narrow and narrow cast. It allows you to use finally constructs where it's a typical RAII pattern of error handling where you can do the cleanup in the finally. So it already provides a whole bunch of types. And we're also looking into adding new types that people talk about. We have a pretty active GitHub community. So recently there have been conversations about stack arrays and dyn arrays. So we are considering writing proposals. And if we do come up with that, it'll show up in the Microsoft GSL library. So that's another thing we will be investing in. And finally, we are investigating opening up the code analysis architecture to third-party plugins. Again, please reach out to us and share your feedback on this. We would build this framework on top of modern AST API. You would have libraries that would allow you to write pattern matching or tree walking. And if there is value in having this platform accessible to the community, I would encourage you to provide us with that feedback so that it can help with the prioritization as we are working on the next set of tooling for static analysis. And finally, I would request all of you to join the fun, give us feedback, give us suggestions. We take the feedback that comes through in the Visual Studio developer community very seriously. So anything that you don't like, let us know. Also, you can reach out to us via Twitter. We have a pretty active Twitter handle for Visual C++. And I'll be available in the Slack to answer any questions that you have on my talk. So feel free to reach out to me. And also, I would request all of you to contribute. It can be an idea on a check, or it can be some bug reports, some fixes in our GSL library. It could be missing test frameworks, or any ideas you have on how we can make checking of code better at compile time. I would be very interested in listening to those ideas. So my request to all of you would be to give us that feedback, to contribute. And I've also provided a bunch of resources here that you can refer back to after my talk. C++ team blog is definitely the big one where everything that we do, all the announcements get made here in the blog. So stay tuned for more safety rules that show up in our team blog. C++ core guidelines has been a pretty effective guiding principle for us to improve the code hygiene within the company. So we would urge all of you to take a look at the guidelines, take a look at our GSL library, where we have a lot of interesting discussions on how we can make this guideline support library more effective in helping people write modern and safe C++. And finally, I would like to thank the amazing contributors that worked on this project. So definitely thankful to the core guideline editors. I've had a great set of interns working on the team in the past winter and this summer. And also, I would like to thank my team for implementing a lot of the checks that you saw today in Visual Studio. And with that, I would like to end my talk, but enjoy the rest of the conference. Again, we have a table at the expo hall where you can meet the C++ team and ask questions. And there is a survey at the end that you can take, and it allows you to win a copy of the flight simulator. And we have a few more sessions lined up. For today, we have the C++ 20 STL features by Stefan. Tomorrow, we have a talk on dynamic polymorphism with metaclasses by Sai. We have a cross-platform talk by Erika. We have effective remote C++ development by Nick. And on Friday, Justin and Michael would be talking about a new open source plugin platform that Microsoft has built. So stay tuned for those sessions and enjoy the rest of the conference. If you have questions, I would love to take those at this point. So I have a question here that says, do any of these checks provide Clang tidy-like fixes that is automatically fix the code to align with the guidelines? That's a great question. So when we think of static analysis, we have a few options in the Visual Studio IDE. So first, we have introduced something called the C++ code linters, and those are the lint style checks that does not require any sort of data flow or control flow or complex logic. And those C++ code linters are built on top of our IntelliSense engine. And that allows you to do a lot of the fixes that you're talking about here, which you would find in Clang Tidy. Second, we also have Clang Tidy integrated as part of the Visual Studio code analysis experience. So you should be able to find Clang Tidy tools integrated. And lastly, for the more involved checks that require control flow, data flow, or path simulation, all those checks, the full power is available with the traditional MSVC code analysis that you're familiar with. So we have a bunch of options that you can choose for, and you will definitely, I believe, enjoy the fixes that come with the C++ lint experience. There is a next question that says, is there work being done or planned work to be done to bring these checks into other compilers or separate static analysis tools? So it's a great question. So one of the things we are doing internally is our ASTs right now are kind of, they are reaching the end of life. They have been in place for the last 10 years. What we want to do is we want to modernize the ASTs because the ASTs are the building blocks for code analysis. And as we are working on it, we are trying to choose a representation where potentially this can work across tool chains. What it means is the analysis we write on top of these modern ASTs can be leveraged across other compilers and tools. But we are into early stages for that. I can maybe give you an update next year on where we are with that effort. But there's definitely work happening to modernize our ASTs in a way that can be used across platforms. Can these tools be easily integrated into the CI/CD pipelines? That's a great question. I think if you cannot integrate these tools into the CI pipeline, it kind of defeats the purpose because like I said, static analysis, its job is to prevent bugs from getting checked in. So I think there are a class of checks you would want to run as you're typing, and those would be lint style checks. Then you would like run slightly more involved checks when you're saving your work or when you're building. That'll happen on your machine. but also it's imperative that you have static analysis checks running in your CI pipeline that prevents your code from getting merged. Think of it like an auto code reviewer, like a bot that comes back and says that, hey, here is an error in your function that you just wrote in this PR and you got to fix it. And from interacting with people across Microsoft, what we have learned is we get a lot better reception when we can flag issues when people are working on it. Imagine, as opposed to that, the code gets checked in and you run these tools and the results come back to you as bugs after a month. By that time, the issue has really gone out of your mind and you're a lot less likely to fix that issue. So definitely we are looking, at least internally, we have started a pilot where we are creating a plugin for Visual Studio Code where you would be able to run these tools on the as you're typing your code, and we are using a viewer to show you these warnings no matter what editor you use. And we also have plans to have a check in the CI pipeline that would prevent you from checking in your code if you have static analysis defects, because we believe that that's when we'll get the maximum engagement from the developers because they're just working on that code. So that's definitely something in the horizon for us. Okay. The next question is, are these tools available in VS Code? So the short answer to that is right now they are not available. But this is something we will consider going forward. Again, if you want to see these tools in VS Code, keep the feedback coming. That just helps us with our prioritization. Like I said, we're already internally working on a VS Code plugin, a VS Code extension that allows you to run these checks inside of VS Code. So if that's something you would want to see in the community, I would appreciate if you can send that sort of feedback to our team, and that just would help with the prioritization. Okay, the next question is, seems like static analysis becomes a lot more complicated with templates, as analysis could return different results for different specializations. How would you deal with that? That's an excellent question. And if you look at the existing analysis that we do, some of the analysis does suffer from this exact limitation that you just mentioned. So imagine you have a template function which has a non-type template parameter, and you are looping on a loop. You're using the non-type template parameter as the bounds of that loop. So when you specialize that template with a value of 0 or 1, which means that loop is never going to be executed, we end up with a warning that says, hey, this is a specialization where you are never going to be executing that loop. That's dead code. However, there are other specializations where you are in fact passing a different value than a 0 or 1, and that loop is going to be executed in those specializations where it's not an easy way to fix it, and it creates some sort of interesting conflict there. So right now, I think the inherent limitations that we have with template is that we only look at specializations, and we don't look when the templates are declared. So all the analysis that happens essentially happens on the specialization. So one of the things we are trying to do is, as we move to the modern AST APIs, is we are trying to say that, hey, can we have syntactic information when you're declaring these templates? And when we have the syntactic declaration, a lot of these rules can move inside to be built on top of that syntactic declaration. So the for loop example I just mentioned, we would not be building that on specialization, but we would build that when the template is declared, and it would eliminate those class of conflicts that you see with templates today. So I think you're right that there are some challenges with templates, but we are trying to make it better for everybody. All right, the next question is, are there plans to enable fallthrough checking in the actual MSVC compiler? An opt-in would be great. So right now, I don't know of any plans to enforce fallthrough within the compiler. Again, if that is something you would want to see in the compiler as an opt-in, I'll take that as a feedback to the compiler team. My friends there would definitely put that on their list of priorities. And again, feedback like this helps us prioritize what you want to see in the compiler, and we can make it happen based on that feedback. But right now, there aren't any plans for having this in the compiler. Okay, the next question is, do the caveats to these C++ checks make them less effective than the safety checks in Rust? Well, I think in my experience, yes, there are caveats, but I don't think caveats are the limiting factor. I think the limiting factor is twofold. First is the implementation of these checks. They are not; these checks are not in the compiler. You can look across the tool chain. So I think the inherent limitation there is it depends on what kind of tools you are using, and you can convince your developers to use. And the second thing is that these rules don't prevent your code from compiling. They're easy to turn off, they're easy to be ignored, and your code will still compile fine. So I think we need to move to a world where we can get more mind share for people believing in the fact that, yes, there'll be a stricter mode that you can opt into. And if you opt into that mode, you will be restricted in things that you can do. But at the same time, you get something in return, which is the code that you generate has certain compile time guarantees like Rust. So I think that's the direction we are pursuing. So I believe that's the world where instead of finding these defects where a rule could find it and they were turned off, we are in a world where because this code is compiled with a strict mode in the compiler, I would like to show these warnings to you preemptively rather than as doing a post-mortem on some security bug that happened out in the field. All right, the next question is, I expect for loops with mutation are more often intended to mutate the source code than a copy. Replace auto with autoreference instead of const autoreference. Maybe warrant based on no discard. Yes, that's an interesting. So this question has two parts. The first part is suggesting to use an autoref instead of a const autoref because sometimes you're going to be mutating the data inside the loop. And we do have a lim check it's a suggestion. And if we look at the later C++ linter, it would look at all range for loops and suggest you use a auto reference for variables that you are taking a copy. So there is a C++ linter check, which is already available today in Visual Studio for that, which I didn't show. And the second part of this question is maybe warrant based on no discard. Again, this is a great question. Before we had no discard in the language, I don't know how many of you are familiar with, we had something here in Microsoft called Microsoft Sal annotation language. It was Microsoft's own way of annotating function signatures to talk about contracts on how those functions behave. And so there was an annotation called must inspect result or check return, which were similar in spirit to no discard. And that's definitely a great suggestion. Now that we have no discard in the language, we should be checking that if you're ignoring the no discard, we should force you to kind of not do that. So that's definitely something we could add to the set of checks we have today. So the next question is, what kind of work would need to be done to implement some form of Rust's borrow checking rules? Exactly one mutable reference or immutable reference, either statically or dynamically. Well, to be honest, I have not looked into what it will take for us to implement the borrow checking in Rust. Like I said, our immediate focus is first fix the lifetime profiles that we have. There are missing cases in basic lifetimes checking, and borrow is something we would look into next. And I would be able to answer this question in the coming months as we look into the borrow checking. But right now, I haven't looked into the existing static analysis framework to figure out what exactly it will take to build this sort of a borrow checking that Rust has in the language. All right. Does it might warn sometimes a false positive? So I believe the question there is, do these tools have false positives? And the answer is yes. If you look at static analysis, there is always going to be false positives because we are inherently trying to walk paths through the program and look for changing properties and trying to make inferences. So there is going to be false positives in any static analysis tool, but we are very conscious of the fact that if we are going to be shipping a check, we want the false positives to be low to a point where the developers find value in them. We use a pretty high bar internally as well to tune down false positives. So yes, there are false positives, but we are very open to hearing about your experience on these checks. And if you report false positives to us, then we will prioritize that and fix that for you. And you can reach out to us in the developer community. We go through every issue reported in that community and prioritize our fixes. The second part to this question is, have you heard about space? No, I have not heard about that. And I believe that was the last question. Thank you, everybody, for joining me in today's talk, and hope you enjoy the rest of the sessions.